December 26, 2004. $227,898 people died in Indonesia, Sri Lanka, Thailand, and many other countries combined. The 2004 Indian Ocean tsunami is considered not only the deadliest tsunami, but the deadliest natural disaster Earth has ever experienced. Around 8 o'clock a.m., a 9.1 magnitude earthquake occurred around 100 kilometers off the coast of Sumatra, Indonesia. This caused something called the wraparound effect. This means that tsunamis formed all around the epicenter, hitting multiple land masses. This event was so powerful and strong that there were effects recorded as far as Antarctica and North America. Throughout this video, we will be discussing the physics behind the movement of the 2004 Boxing Day tsunami. Let's start from the formation of a wave. Waves carry energy through small or large distances using vibratory motions. When classifying waves, they can be broken down into electromagnetic waves and mechanical waves. In this case, a tsunami is a mechanical wave because the energy transferred must travel within a medium. Waves are then started because of a source. During the Boxing Day tsunami, the source of the tsunami was the shift in the tectonic plates. This is when one plate moves upwards and one moves downwards. This creates a displacement of the ocean floor that results in the water almost lifting up in a vertical motion. As a matter of fact, a 1,200 kilometer section of the Earth's tectonic plates were displaced during the 9.1 magnitude earthquake. The large surface area of the plates causes waves to move in all directions away from the disturbing force. From there, the applied force from the tectonic plates transfers into energy and into waves as they disperse from the disturbing force. This is key to understand because it is not the domino effect as a result of the water mass that moves the water, but rather the energy. Now, the wave is formed. The basic components of the wave include the crest, which is the highest point of the wave, the trough, the lowest part of the wave, the period, the time for one complete wave, the frequency, the number of cycles completed in 1 second, and the wavelength. Wavelength is the distance between 2 points in a wave which are at the same phase. For example, the distance between 2 crests or the distance between 2 troughs. The wave is also composed of the amplitude, which is the distance from the crest to the middle of the wave, and is directly proportional to the energy the wave contains. Therefore, the more energy a wave has, the bigger the wave. It was estimated that the amount of energy transferred within the waves of the Boxing Day tsunami were equivalent to 23,000 Hiroshima bombs. That's one big wave. Now we have discussed the formation and components of a tsunami. So how fast does a tsunami move across water to land? The universal wave equation can be applied to any kind of wave, whether this be sound, light, or water wave. The reason this wave equation can be used universally is because all types of waves have very similar aspects to them, including speed, frequency, and wavelength. This equation is demonstrated as V equals F times lambda. V is equal to speed, F is equal to frequency, and lambda is the wavelength of the wave. We use the calculated wavelength of the tsunami, which is 350 kilometers. However, we were only able to collect the magnitude of the wavelength and not the frequency. So after researching extensively, we decided to use a realistic fictitious frequency of 6.0 times 10 to the power of -4 hertz. The frequency is smaller in size because the wavelength of the tsunami is large and therefore it requires a lot of time to complete one full cycle. We times the two numbers together and got a value of 0.21 kilometers per second, which is equivalent to 756 kilometers per hour. However, this equation does not take into account the fact that the tsunami can be affected by the height and how said height affects the speed of the wave. This is because its wavelength is larger than the depth of the water of its epicenter. Therefore, we use the shallow water wave formula, c is equal to the square root of g times h. In the formula, c represents the phase velocity, which is a fancy name for the velocity we calculated earlier. G is equal to gravity, which in this case is negative 9.81 meters per second squared, and H is the depth of the water from sea level. Therefore, H will always be negative as tsunamis are created by disturbances under the water. We can also assume that the gravity stays as a negative value. This is because in this situation, gravity is working on a vertical axis. Gravity acts on the waves and causes the wave to move towards the center of the Earth due to gravity working on each of the water molecules. It is assumed it stays 9.81 because it is in Earth's atmosphere and is near the surface of the Earth. By using this formula, we are able to calculate the approximate phase velocity of the wave based off the changing ocean height. For example, let's try the velocity when the depth of the ocean was 1,000 meters. After plugging in the values under the root and multiplying them, we got an answer of 99.045. Then, by using unit analysis, we ended up with 357 kilometers per hour. The approximate phase velocity calculated by the shallow water wave equation can be used to prove that as tsunamis approach the coast, they slow down. A proportional to 1 over b to the power of 1 over 4 can be used to calculate the change in amplitude as the tsunami approaches the shore. In this formula, b represents the depth to the bottom of the ocean and a represents the amplitude of the wave. Using this formula, we can mathematically prove that as the tsunami approaches the shore, its amplitude will increase in size, which is the reason why it is much harder to detect tsunamis until they are close to the shore. This is because they barely show above the water until they begin to rapidly approach the shore, in which case they suddenly grow to massive sizes. But the real question is, how can we stop something that is so destructive and so powerful? The answer is, we can't. But we can slow it down. One method is demonstrated during the Japan tsunami, a seawall. A seawall is generally made out of concrete and is bolted into the ground. This serves as a great way to slow down the impact of the tsunami. But why does this work? Newton's first law, the law of inertia, states that objects like to stay either in constant rest or constant speed. In some cases, seawalls have more inertia than the water itself, and will therefore stop the wave from surging into land. Of course, the water finally builds enough volume and is able to topple over the seawall, but it gives citizens more time to be able to escape the wave. That was the physics behind the horrible, devastating wave that led to hundreds missing, thousands dead, and millions of dollars of damage. It's fascinating, but terrifying, how water can be our best friend and our worst enemy.